So just a brief review of examples we've done so far before we wrap up heat transport, hopefully today. Okay. So our first example was example of viscous heating, and it had this standard assumption or standard procedure that we're going to do, where you basically assume that you have a velocity distribution given, and then given that knowledge, you plug that into the shell balance for our combined energy flux, and then we solve the problem. Typically, what we're looking for, like while we're balancing energy, we can't really solve for energy. We're always solving for temperature distributions, and that's where most of the work is actually involved in calculating this. So in this particular problem, we had inner cylinder heated at T0 and outer at TB, but there was also fluid moving within a very thin shell, which causes a lot of friction and a lot of heating as a result. So as a result, we don't have a standard linear profile of temperature between T0 to TB, but we have some certain nonlinear profile, such as depicted here, that is calculated at the end with these equations. So it has sort of like a parabolic component to it. Okay. Now, second problem was both example with the chemical heat source and also with the porous medium. We worked with it in averaged sense, so it was basically ultimately one-dimensional medium, and we assumed velocity of the fluid to be Darcy velocity moving through the porous medium. We don't know all of the details and don't necessarily want to know all of the details. However, there is a lot of utility in any type of reactors, because spheres or having spheres provides extra reaction surface that you need for certain catalysts, and then basically then you need to know how to model sphere packs, right, and upscale them. Okay? So here we actually had a source, so we couldn't necessarily ignore that enthalpy term, and it is important to remember this formula for integrating enthalpy. This is borrowed from thermodynamics, but for ideal gas, you're going to have sort of a linear function, and for just in terms of temperature, and for any other fluid of constant density, you're going to have a term that is linear both in temperature and pressure. After that is done, basically we got something at the end of it. We got something like this. So there's a normalized temperature theta, okay, and normalized length z, and at this d theta dz is n term, which is just a constant computed from everything that we know, f of theta, and f of theta comes from that source term, so it's presumably known. Okay. Now, in terms of, once one would actually solve this for theta that is just linear, okay, f of theta just being theta, then you would get something like this. So in terms of normalized temperature, and for different n terms, you would get like sort of a different end zone temperature. Okay. All right. Now on your own, please do 10.6 and 10.7. Composite walls is something that is a standard problem, and as well as cooling fin. So cooling fin, as you're going to solve only for one, but it's again, you have a geometry of cooling fins has like multiple sort of wedges like this going around. Basically, again, it provides extra surface area for cooling, right? So that's one thing that is important in various industrial applications. Okay. Now our example that we just finished before this was the forced heat convection, where we basically had a source from the outside. A standard application in petroleum engineering would be warming up of a pipeline. Well, assuming a very small pipe that has laminar flow within. Okay, so that's something that we understood about this problem. We did not solve it for turbulent case. So basically, and for turbulent cases, we're not going to go into it, but essentially you would have friction factors equivalents for heat flow as well. So strategy is basically, again, assume known velocity distribution and then use that distribution in energy shell balance. And now we have both Z term for our convection of fluid and R terms for basically the heat transport. So those two are basically orthogonal to each other. So we don't have the classical situation where we have flow only in one direction and dependence on the other direction. So it's a little more complex than that. So basically, ultimately, I'm just going to go to the final thing that we got. So we do have to help ourselves here with the momentum balance that basically zeroes out one of the terms. But regardless, I still have my convective term, which is basically moving at velocity vz, and that one carries also the derivative of the or change in temperature in z direction. Okay. And on the other side, I have the second order derivative of temperature in z, as well as this is all due to molecular transport, as well as the major part of the heat transport here in our direction. Okay. So you should know how to recognize, so basically if there is a Vz term here, obviously this is the convective term that moves with the velocity or with the fluid velocity, and the others are due to the molecular transport. Okay? So that's something to basically, when you look at the equation, you should kind of know and recognize both directions of the transport and the types of the sources of the transport. And one thing that we noted, we didn't actually look into that, but basically if you ignore this z direction term, okay, then you can actually solve this equation analytically. And you can actually take, I think there's one of the solved problems in the back of BSL that involves this. Okay, so now we're just going to go over equations of change, which is essentially shell balance, but we do have time incorporated in there as well. And we're going to solve one more problem that is kind of more interesting. It's a Maxwell solution for spherical geometry. You can't have a sequence of solutions unless we sample all of the possible geometries that we're dealing with. So we started with sort of slit-like geometry, then the second problem was a tube, and now we gotta do a sphere at the end. Okay? So things would not be right. All right. So basically, we're gonna approach the same. We are gonna approach things the same way as usual. So the rate of energy, either accumulation or decrease, is inside the fluid element, is the net rate of energy that is basically quantified by the combined energy flux vector, work done by external forces, and net rate of energy production if we have reactions or anything of that sort. So if this is my sort of a volume element, how about you actually take a piece of paper and wake up and translate these words into symbols. And we're going to omit the production term. We're just going to do without the sources right now. So how would I write down the rate of kinetic and internal energy accumulation within fluid elements? So basically my one based on the balance, one is going to be equal sum of 2, 3, 4, and 5. Are we ready for? So this is a self-test, so you self-grade. So first term, so it's the rate, therefore I have d dt. This is the energy density term, and since it's a density term, I gotta multiply with volume of the element to get the actual amount of energy. And now we're looking at the energy and as quantified by E, vector E, that enters and leaves through this volume boundaries in x direction. So that is our Ex evaluated at x times the area, which is delta y delta z, minus Ex evaluated at x plus delta x, also times the area. And now I have two more terms that are basically similar. They're just in y direction and z direction. Okay. And then at the end, I have work done by the external forces. So I have gravity, basically mg dot v, right? M is rho times volume of the element. G, so that's my gravity force dot velocity. Yeah, okay, that's basically the ballast. Now we just have to figure out the differential equation, and per usual, we divide by the volume element, okay, and make those delta x, delta y, delta z small. This is not a call, this is my phone imagining things. Apologies. Okay, bye. Alright, so when we divide by volume and take the limit, what do we get for this term? These three terms. My favorite operator, divergence. So dx, dex, dy plus dey, y plus dez, dz. That gives us divergence of E plus rho gd. Okay? So not many surprises. It basically looks simple because we didn't write what E stands for. Okay? But we really need to solve for temperature, so this needs a little more work. Our E is, this is the original definition that we used, basically with just internal energy here. And then we have the second form that has enthalpy, where basically the pressure part from the molecular forces jumps over into the enthalpy term. Oops. Right. So if I have actually stationary solid, then the volume part is, the velocity terms are easy because they're zero, so that simplifies things greatly. So just if I look at my E, so if I do divergence of E, then for velocity equals to 0, first two terms disappear, and I only have Q, right? Now Q is minus K gradient T, right? So what will I get when I take divergence of that? Laplacian. So divergence of a gradient is Laplacian. Divergence. Repeat that 5 times and you'll remember it really well. Divergence of a gradient is Laplacian. It's very careful. It's very useful for these quick estimates here, because again, Laplacian is something that is standardly available that you can quickly look up in the back of the book. So basically, So here, it's interesting. So basically my equation, if I just go back to it, right, then the only thing that is left for stationary solid, so this would be 0, right? These two terms are 0. The only thing that I have here is Laplacian term multiplied by k. And here velocity would be 0, so we just have change of internal energy, right, is equal to the Laplacian of t. Okay? Now, so one thing that I could do is we already had the equation of change for internal energy that we worked through while working through chapter 7. And that one basically just involved 1/2 rho v squared over there. So if we subtract the two, we can actually get the equation of the change for internal energy only. So this is just for you to have kind of as a reference. So basically, this is the equation of change for internal energy that we had previously. And then there are certain terms that I can basically then recognize in there, right? There's one term here. There's this red term, okay? This one, and this one. Okay? So basically, if I subtract the two, I will get something like this. So this is my equation of change for internal energy. Basically, I have the convection term for internal energy. This is the heat term, P, and divergence dot V. And this is, if you remember, do you remember this operator? Ever so slightly. So if I have two matrices, I multiply each corresponding element in matrices, and then I sum them all up. So this is one big sum. So it looks scary, but it's simple to compute. The way matrix multiplications go, that one's simpler, right? All right, so basically, I could also do a material derivative formulation if I transfer this term on the other side. Then that's actually material derivative of rho u hat. Does everybody see this? This term plus this term, right? So this is just a shorter way to write the change of internal energy. And then for Newtonian fluids, I can assume that we, oops, hi, my mouse is not, or my, so for Newtonian fluids, involving some thermodynamic equations that we're not going to go into here, you can just use this equation, assuming you have equations for state for P and you have equation for CP. Okay? And if I have ideal gas, then my viscous term will disappear because ideal gas does not have viscosity. All right. So those are just, oh, sorry, if you needed to write that. So those are just equations that you can use. You can always start from that shell balance equation and go from there, but these are just some shorter versions in case you need them. All right, so we're going to solve one more problem. It's going to be simple in the sense that it's going to be stationary, so there will be no velocity. But it's going to be spherical problem, so there will be a little bit of a difficulty in solving the equations. So we will actually have to, from the boundary conditions, we will have to guess what the form of the temperature distribution is before actually solving for it. So let's get going. Whoops. All right. So this is example. Let's see how it. Oh, okay, good. So this is, you can also see BSL problem 11B8. This is so-called max, whatever it is that I did in there. Nice. I hope. It's a tilted sphere, except that for sphere it doesn't matter. Okay. Fabulous. All right, let's try this again. So I did actually reboot and update my computer this morning because we know what happens when I don't, right? But then that probably resets some settings, or I don't know. This morning I happened to touch this computer in a completely new way. So it's some shortcut for something that I don't normally use. this is meant for artists, so they do all kinds of weird stuff. And I'm just like, all I need to do is write. Okay, I don't need fancy coloring. I don't need anything. So very, look at that. Radial menu. And you would think that by now I would have figured out a steady hand that moves only a certain way, but apparently not. Okay, so this is Maxwell. Analysis of heat conduction in an infinite domain with spherical inclusion. So this is my spherical inclusion. It has radius r. I'm going to put my z direction because that's going to be my direction of the temperature gradient. But really this has, at some point away from sphere, I have r and theta. What is the discussion about? Oh, Maxwell's analysis of heat conduction in an infinite domain with spherical inclusion. Isn't that clear? Come on. So I'm going to have its spherical inclusion, meaning that these two, the sphere itself and the surrounding, have different thermal conductivities. Otherwise, why would we look at it, right? So this is going to have thermal conductivity K1, and outside is going to be thermal conductivity K0. And my first boundary condition is T equals to T0 at R is equal to 0. I'm moving it again. And it's some sort of simultaneous of me attaching this little thing here. So excuse me, excuse the tilt. I can apparently also zoom in and out. I just don't know how. It's something, again, if I touch and then this. No, now, no. Oh, never mind. Okay. And I have a constant temperature gradient away from the sphere. Look at this. Okay. I have somehow specialized touching. This time it's not drawing while I'm touching with my hand, but now it's doing something else. Now, if I only knew. So this is away from the sphere. So that I'm going to quantify that that's my boundary condition when not r, lowercase r tends to infinity. So I'm going to look at the steady state solution. So I'm not going to look at anything complicated, at least in terms of equation. So what my basically equation comes down to is, since velocity term is 0, what's the only one left? Q. Yep. So basically divergence of Q is equal to 0. And as just mentioned previously that means that Laplacian of t is equal to, well, negative of it, but now one thing that is important to note is that this k is different in different materials. So we're actually solving a simple equation. It's just that we're going to have to match the boundary conditions. So it's really Laplace of t is equal to 0 in each material. And I have to do appropriate matching on the boundary. Right? So looks simple. Let's get at it. Laplacian, this is Laplacian in spherical coordinates, right? So mental note, go to the appendix and look up Laplacian in spherical coordinates, okay? It's not your txx plus tyy plus tzz, right? None of that. So that basically, my notes say that it's table A73. And I don't have any phi dependence. I really have depends. So since my flux is sort of dt dz, the gradient is in z direction. However I slice this in phi direction, I get the same. So I have no phi dependence. But I do have theta. So what I get then for Laplacian is 1 over r squared ddr, r squared dt dr, plus 1 over r squared sine theta, dd theta, sine theta, dt d theta is equal to 0. So that's my main equation. I'm going to label it as a star. Now, is my t a function of r only? Theta only? Is it? I kind of have to go around that sphere, right? Because it's not going to be straightforward transport because of the difference in the conductivities. So no, t is t of r theta, okay? So I can't really kill any of these terms. But what I can do is look at the boundary conditions and see whether I can simplify. So my first one says, okay, t is t0 at r is equal to 0. That doesn't really tell me all that much. Let's look at the second one. My second BC says dt dz is equal to a. Well, and also that dt dx and dt dy are equal to 0. So I have to look at t of r theta, and this does not tell me about r and theta directions, so I have to translate this. What does this mean for the gradient in spherical coordinates, right? So again, gradient is gradient. I choose to look at it in a certain coordinate system, and that gives me actual numerical values sort of tied to that coordinate system. And I know that I can go in between vectors in different coordinate systems by basically having an appropriate matrix that I multiply with. Remember that? So we do have actually those terms in the back. So basically my gradient or r coordinate of the gradient in terms of the Cartesian coordinate systems is this is in appendix, the formula basically that ties any vector in r, theta, and phi with any vector in x, y, z. Okay? Again, gradient is gradient. I just choose to look at it two different coordinate systems. So this is based on the appendix sine theta cosine phi dt dx plus sine theta sine phi dt dy plus cosine theta dt dz. Again, gradient is gradient, so I can look at it in any coordinate. And this is something that just relates vectors and their representation in spherical coordinate system to that in x, y, z. So this is now 0. So this is simply a cosine theta. I'm going to write it here, a cosine theta. Oh, okay, there was just a delay. Okay. Yes? So now we do the same for the theta direction. So my t in theta direction, also known as dt d theta. No, actually 1 over r. And I have a 629. That tells me that this is cosine theta cosine phi dt dx plus cosine theta sine phi dt dy plus, or rather minus, sine theta dt dz. And this is minus a sine theta, because this is 0 and this is 0. So I have just to, so my dt dr is a cosine theta, and my 1 over r dt d theta is minus a sine theta as r tends to infinity. That's my boundary condition. So all I've done, all of this work, was just to translate my XYZ coordinate system boundary condition into spherical coordinate system. That's all I've done. 2 points is, well, gradient is gradient. I can choose to look at it and change my coordinate systems, and I know how to do that. But one thing that we shouldn't remember, and I actually inadvertently made that mistake while speaking, is like, okay, the theta portion of a coordinate is not just dt d theta. Okay, I have to look up what my gradient means in spherical coordinate system. So just mental note, just look all of the things up. Don't assume you know the formula. Look what is gradient in spherical coordinate system, and also how to translate any vector from spherical coordinate system using its coordinate in xyz, because that's what was given, right? My z coordinate for gradient of t was given, right? And the others assume 0. So there's plenty, it's conceptually simple, but there's plenty of room for error if you kind of assume you know something and you just go and write it down. All right, so now basically what we actually want to do is we want to simplify our life and assume a functional form or sort of a separation of variables form for t. This is a common practice for partial differential equations. If you have t of r theta is, t is a function of r and theta, you assume that it's t is one function of r times another function of theta. Okay? So technically we are looking at sort of a method of solution. So t of r theta is some function of r and some function of theta. So question is, by looking at, so here I have derivatives with respect to r and derivatives with respect to theta of t. Is there a way for me to guess one of these functions? So what would dt dr be? It would be just, look at that. In my tilted way, it would be f prime of r g of theta. And my dt d theta would be f of r g prime of theta. Let me see if I can undo the tilt. Oh, come on. I should have done that already. No? Oh, never mind. dt d theta is f of r g prime of theta. And maybe just to make it easier to look at, minus AR. Oh. Wow. And no, you cannot undo the tilt. I can just keep doing. I'm gonna have to reset. So I did update my computer this morning, and I'm wondering if this software updated somehow, the vacuum software. I'm just gonna do new.
Why don't you rotate your 2 fingers?
I don't know where to rotate. I never rotate.
Just cancel that.
Yeah, oh, okay. So with 2 fingers.
Yes.
So somehow
So if you've got,
touching
like,
with 2.
your hand and your point, then it's counting as 2.
Gee, okay, thank you. Okay, so basically, so what is the derivative of cosine? Minus sine. So maybe, since this is done as r is equal tends to infinity, I'm not going to go and assume function of r, right? Because r is changing. But my theta in this boundary condition is not changing. And I have cosine theta and minus sine. This is essentially g prime of theta for g being cosine. Okay? So essentially I can assume T of r theta is f of r cosine theta. Because r is changing, tends to infinity, so it's dangerous to assume f of r, okay? And also cosine theta prime is minus sine theta, so it's kind of staring at me, waiting to be recognized. So this is it really. From this on, it's just like plugging things in, give or take. So basically, we're going to, and we can actually, oh, since all of these are derivatives, technically, we're going to assume to be sure a constant here, C0, because otherwise I'm just looking at derivatives. I don't want to miss anything. So my dt dr is f prime of r cosine theta. My dt d theta is minus f of r sine theta. And then I have that term d theta of sine theta, dt d theta in my initial equation. That is minus f of r sine theta cosine theta. So when I plug that into my initial equation, that's that starred equation where I had a Laplacian. Then I have 1 over r squared d dr. Here we go again. Of r squared f prime of r cosine theta. Cosine theta. Plus 1 over r squared sine theta minus 2f of r sine theta cosine theta is equal to 0. So I can actually multiply that times r over cosine theta. Minus 2f of r. It's also very slow in reacting. Huh. Okay. So basically I have r squared f double prime of r plus 2r chain rule on the first term, f prime of r, minus 2f of r is equal to 0. Quite frankly, if you guessed right, then theta dependence will basically just get removed after plugging things in. So just give me 1 minute to comment on it. The way this is solved is by looking for a polynomial. Okay, so my f of r is r to the n, and then you plug that in, dot, 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 n minus 1 times n plus 2 r to the n has to be equal to 0. So your either n is 1 or n is minus 2. So general form of f of r is c1 over r squared plus c2r. So my general form of r and theta is c1 over r squared plus c2r cosine theta plus c0. So I have actually 6 of these that I'm looking for. C1, C2, and C0 inside the sphere, and C1, C2, C0 outside of the sphere, and I gotta match the boundary conditions. Okay? That's essentially then just the technicality of working these out. Okay? So 6 parameters inside and outside the sphere. This was the major component of solving for this. Okay? That essentially concludes our heat transport. I used to have a plan of having a quiz on heat transport last Friday, but that kind of got postponed. So I'm going to do a quiz on Monday. Okay? Again, a short 5 to 10 minute quiz. I actually just plugged in, and I was just trying to zoom through to get. But basically, if you we were actually looking for d theta of sine theta dt d theta. So you do d theta of sine theta. What is dt d theta? So there is a minus f of r sine theta. So you do basically d theta of sine squared theta. So that gives you, since it's sine squared, minus 2 sine squared cosine. And f of r stays the same.
You can see the fracture trajectory more clearly here than normal strain field. So we basically demonstrate with these experiments that differences in mechanical properties between adjacent layers can actually influence the trajectories of induced fractures, and that in layer rocks with small stress contrast, material properties can impact fracture height growth. We also see a tendency for an induced fracture in a soft layer to stay within this soft layer and to migrate into softer layers without difficulty when the fracture is induced in a hard layer. We would expect fractures to become more affected by the material heterogeneity when we lower the applied stress contrast. And lastly is the relative layer thickness and layered material can affect the fracture growth. In the second set of experiments, we look at how hydraulic fractures grow when we have regions of high pore pressure and multiple fluid injection sources. In this first test, we have a homogeneous specimen with 3 holes. I applied a far field stress of 65 psi in the x direction, but I only injected the fluid in the center, in the middle hole, by keeping the top and bottom holes at atmospheric pressure. And as we expect, the fracture follows the applied far field stress direction. Next, I used the same specimen and I applied a relatively higher far field stress in the x direction, but injected the fluid in the 3 holes simultaneously.